we are going to continue from where we ended last time on electrical power system protection and dynamics. So we saw the introduction aspect of the power system protection, and then we went into the various types of faults, the types of faults in electrical power system, and then we saw the various fault detection methods and the fault location techniques. So today we are going to continue with the power system protection devices. We have several power system protection devices, and these can be used in the various electrical power system components, compartments, because we know electrical power system is divided into various compartments such as the generation, transmission, distribution, and the consumers. Based on these various compartments, we have several power system protection devices that can be used to protect either the generators or the transmission line and the transmission line components and the distribution line components as well, and also the level of the load. So this can be classified based on their voltage levels classification, because we have the various devices for low voltage classification. For example, the fuses. We have low voltage fuses and we also have high voltage fuses. So that's why we want to classify these, right? The types of components that are used in protection of low voltage are not necessarily the same that are used in the protection of the medium voltage line. You have some of them that are the same, but we have some differences when it comes to transmission and distribution lines, as well as the high voltage applications. So for the fuses, low voltage fuses, we have different types of low voltage fuses. And these fuses, normally we know that fuses are used to protect against overcurrent. Overcurrent. This overcurrent can be due to short circuit or overload. And these fuses here can be classified as well based on the range of current which they can support or protect. Yeah. So we have the various fuses here. The reliable fuse, which is shown in this figure A, is a reliable fuse. You know, the reliable fuse has a fuse element that links the two copper terminals, which are indicated here and here. So this fuse element is simply a wire, and we know that it operates based on what the heating effect, in such a way that when there is an overcurrent, the heating effect increases, because we know that current generally has some effects. We have the heating effect, magnetic effect, chemical effect, but applicable to this variable fuse is the much more of the heating effect, because when there is an overcurrent, what happens is that the heating effect increases, and so it melts the fuse element, right? So you have most of these applicable at the consumer units of your homes, right? If you notice at some of the consumer units, most especially those old consumer units, you always see a fuse element there, in such a way that when there's an overload, the fuse element melts, and you can replace it with melting to protect you, to disconnect you from the supply due to that overcurrent, so that your equipments at home or your loads at home shouldn't be damaged, right? So we have another type, which is the cartridge fuse. This cartridge fuse as well is also used in your consumer units at home. You can always see them there. It's made up of a cartridge. The cartridge is just like in the form of a bullet, right? Yeah, and it also has a fuse element internally, but it is closed. It is closed. We also have these cartridge fuse for low voltage electronic applications that are used in electronic components, electronic devices, to protect against overcurrent. So it has the same operating principle as the reliable fuse, and it is also rated. You have these fuses are also rated, but the range of current are very small ranges of current compared to the third one, which is the high rupting capacity fuse or the high breaking capacity fuse. Even though it is for low voltage application, but it has the ability to support a current of 1000 amperes. So if you have, for example, installations with high amount of current, and you need to protect them against an overcurrent that is greater than this is terminal current. You can use the high rupting capacity fuse or high breaking capacity fuse. So these are the low voltage application fuses. So we also have the high voltage, the medium and the high voltage fuses here. Most of the times you have seen this on transmission lines, on distribution lines, as well as on distribution lines. You as well as transmission lines, right? You will see here the cartridge, sorry, the fuse element indicated here. You can see it here as well. So this one is used for high voltage, medium voltage of up to 33 kilovolt and higher voltages. So these are the fuses that are used for medium and high voltage applications. Then now we have the circuit breakers. We know that circuit breakers are used to protect against what? You have short circuit, overload, right? We also have circuit breakers that are designed to protect against earth leakage. Mhm. So here we'll see the circuit breakers that are used for low voltage application, right? You can read through these notes, but here we have the various types. We have the MCB, which is a miniature circuit breaker. This one has a rated current of maximum 100 ampere. So based on the various types of low voltage installations which you have, you can see have circuit breakers of might be ranging from 0 ampere, 10 ampere, 20 ampere, 32 ampere, 60 ampere, 100 ampere. Then we have the molded case circuit breaker. This one, the molded case circuit breakers. These ones are mostly used for industrial applications to protect what equipment in industries, right? Or probably workshops and so on. And it has a rated current of up to 1600 ampere. And then we also have the air circuit breaker. This is used for heavy current applications of up to 60,000 up to 6,000 ampere. And these various circuit breakers operate using the thermomagnetic operation, either the thermal and magnetic operation. Okay, so these are the low voltage circuit breakers, some of the low voltage circuit breakers that you have, right? You have the other types that are given here, the residual circuit breaker, the uh, 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 earth circuit breaker, and so on. You can read that. Those ones mainly incorporates as well the aspect of earth leakage protection. Then now we'll look at the high voltage circuit breakers. These are the circuit breakers that are used for medium voltage and high voltage line, be it at the level of transmission, that is primary or secondary transmission, and primary distribution as well. And then we have the various types of circuit breakers here are classified based on their level, based on their arc quenching mechanisms, because we know that during interruption, that means when the circuit breakers are opening or closing, it generally produces an arc, because an arc is produced when the potential gradient across the air gap is very, very high enough to ionize the air particles around, and so it produces the arc. So this arc is very detrimental because it might destroy the circuit breaker and also cause it what? Also might be cause a fire outbreak, or an over voltage, switching over voltage, and so on. So we have the various high voltage circuit breakers are classified based on the arc quenching mechanism or arc extinguishing mechanism. So we have the oil circuit breaker, we have the SF6. SF6 here is what? Sulfur hexafluoride. So sulfur hexafluoride is a gas that is used to quench that arc, right? And then the oil circuit breaker uses what? Oil to quench the arc, because the contacts here in oil, when they close or open, the the arcs cannot be produced. Then the vacuum circuit breaker, in a vacuum there are no air particles, so they cannot be an arc being produced because they are not air particles to be ionized. So the breaker contacts can open and close without the arc being produced. We also have the air blast circuit breaker. So the air blast circuit breaker here uses what, or pressurizes air. It pressurizes air to do what, extinguish the arc in such a way that when air is forced at a high pressure, the arc is forced to quench. So we have those various circuit breakers, and here are their various schematics or figures. So this is that of the minimum oil circuit breaker, right? So you have them, the various parts there that are labeled. Then you have the sulfur hexafluoride circuit breaker, SF6. Then you also have this, see an example of an FF6. And so it has its own advantages and disadvantages. So you can read that. Then we have the vacuum circuit breaker, this the figure we've shown here. Then the air blast the air blast circuit breaker. Here is it. So the air blast circuit breaker, we have different types. The different types here are classified based on how the air is projected on the arc path, quench the arc. So we have it represented in the figure here, figure 10. So we have the various directions of the air, how they are projected in order to quench the arc. Okay, then we move to the next instruments, or the next power system protection devices. Here we call them instrument transformers. So we know that transformers, normally you generally know that transformers here are used to step up or step down voltages at the same frequency. But now this is a different type of transformer which is different from the normal transformer you know. The normal transformer you know, we call it what? Power transformers. We call that power transformers. But these ones, these special transformers here that are used in protection, are called instrument transformers. Instrument transformers, because their operation is that they are used to measure either current or voltage, and their measurement are essential in power system protection, because to protect a system you need to measure to actually know whether probably the current or the voltage on the line is okay or normal, right? So we have two main instrument transformers here. The current transformer is used to measure current, and you also have the voltage transformer. The voltage transformer is used to measure voltage. So here is the figure of the current transformer. You see the current transformer here. One way you can differentiate the current transformer from the voltage transformer is this bushing here. You see the bushing of the current transformer is down. Then you have the core of the current transformer here at the top, in such a way that this core is this core is an iron core, or any other type of core, which the conductors passes through that core. You're going to see a schematic representation of it below. So that's the easiest way you can identify a current transformer from a voltage transformer. The bushing of current transformer is down and the core is up. Then the conductor, which the current transformer is to measure the current flowing through it, is it passes in the core, right, of that current transformer. So we look at the voltage. Okay, here's what I was trying to explain. Here's the hollow core, which the current conductor, carrying conductor, passes through. So we consider the current carrying conductor carrying the current, which is I primary, or the primary current flowing in the conductor, right? Then around that core, you have a winding that is wound around that core in such a way that we know that as that current carrying conductor in the primary conductor is carrying current, there is a magnetic field that is produced around the primary conductor, and this is linked and cuts these windings on that hollow core, and so it produces secondary current, and that secondary current what you utilize in order to actually determine the primary current on the line, because what you're utilizing here as a secondary current is the current here has a lower value. But now, how can you know the primary current on the line? You can know the primary current using what uh, 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 the turns ratio of that primary of that current transformer, right? The turns ratio is given to you by the manufacturer when you buy the current transformer. So you can make what IP, which is the primary current here, the subject of the formula to get what the primary current in the line, because you are going to have IS, which is the secondary current which you are reading, right? Okay, so we have the different topologies here of the current transformer, how they are represented. ANSI is American standard, and you have the other topology. So whenever you see these images or these representations, all of them represent the current transformer. They are the same. Then the current transformer here, so that one was a single phase, how the single phase line can be represented, if single phase current transformer can be represented. So here now we represent the three phase current transformer. You know the three phase line has three phases. So you have three windings of the of three current transformers, and now in, they are interconnected either in star or in delta. So this forms now a three phase current transformer. So you have the star connection. You know the star connection, all the output terminals are short circuited here, right? Not all the outputs, all the terminals of either the output here or the input here are short circuited, right? So you short circuit that, you have a common terminal that will give you a star. So any side you can use any side either as input or output. Okay, then the star, you know the star. For the star, the input of the output of the other winding is the input of the next. The output of the other winding is the input of the next.